We can hear you fine.
Recording has begun.
All right. All right. Hello, everyone. Can you hear me? Probably you can because I yell. Hello, everyone, to EC Colloquium 801. My name is Dima Farfurnik. I'm an assistant professor here in the department. My field of research is quantum photonics. So I'm going to be the instructor of this course together with my colleague Dr. Abraham Vasquez Gardado. But the most important person here in this course is not any of us. It's our good TA, Chene Otley. And any concerns that you have or any questions that you have about the administrations of the course, please reach out to Shane and she will be able to help you. If for some reason Shane was not able to help, or if you have questions not about administrations of the course, but about the science or something that the speakers have said or something like that, then you can reach out to me or to Dr. Abraham. So before we introduce our speakers, I want to just briefly mention a couple of administrations of the course for those of you who are taking the course for the first time, but also for those who already took the course and previously. So as you may know, we have the Moodle page of the course. If you go to Wolfware, then you can log into EC 801, and you have different resources about the course. You have the course syllabus that describes, all the administrations of the course. You have the perhaps the most important thing is the colloquium lineup, the lineup of our speakers. So we have great speakers from academia, from industry, even from government agencies. So you can see the list of speakers here, and also they're posted on the ECE seminar website. So you can look in there and see. Now, in terms of, okay, what do I need to do to pass the course, all things like that, we have 14 seminars scheduled, and to pass the course, you guys need to not miss more than 3. So currently, not more than 3 means 14 minus 3 is 11. But if for some reason we cancel a seminar or something, it's fine. You don't need to do 11, So it's very important for you guys to take the seminars in person, to actually come here and listen to the speakers, because you respect the speakers that come from different areas of the States, and also you are able to interact with them. So as you can see, these talks are also streamed on Zoom, but we prefer that you come in person. So we prefer that you guys don't participate on Zoom, and we limit the number of Zoom attendance to 3 this semester. Unless you have very specific and unusual problem. For instance, there are students who are not in the States and are about to graduate, and they only need the seminar course in order to graduate. So for those students, we say, okay, you can take the course on Zoom. But if you are around and can come in person, we will ask you to come in person. Now, there are also other scenarios when you guys cannot attend for any reason our usual Friday colloquium. So what you can do instead sometimes is to attend a different seminar. For example, a seminar of another department, like the physics or the chemistry or the College of Textiles or whatever. Or you can also attend a topical seminar, like if there is a closed seminar, an AI seminar, a quantum seminar. So you can basically substitute 3 seminars of our regular, colloquium series on Friday with 3 other seminars from different places. I can log in as a student here and show you that there is here, there's supposed to be here, not here, but in a top left here. there is alternative seminar form. You just fill out this form, which kind of seminar you want to attend instead of the Friday colloquium seminar. And if it's reasonable, Shanae will count it as a seminar for you. A couple of other kind of things that are new this semester is, first of all, unfortunately, we don't have enough budgets to supply snacks and coffee for you. We deeply apologize. And if we end up getting budget, we will try to make it happen again. But we do have 2 new additions. One addition is that for speakers that are going to be external, okay, not from inside NC State, but speakers come from elsewhere, we're going to have a special sessions that are only for students and postdocs. Like usually it's going to be held here like on the 3rd or 4th floor at 3 p.m. And professors are not allowed to come. So the idea is that you guys can come and talk to the speaker directly. If you want to gossip about your professor, you're welcome to do it. But if not, what you can do is the colloquia, we arrange the speakers in such a way that they come and give general talks. So if somebody comes and gives a talk about AI, then even people who are in power electronics or quantum or bio should understand what that person is talking about. But for those of you who are particularly interested in the field of expertise of that particular speaker, you are strongly encouraged to attend these 3 p.m. sessions and talk to the speakers directly, dive into more technical details and things like that. This is also an opportunity for you to, to learn from the speaker's experience and get advice. Okay, what does it mean to work in a national lab? What does it mean to be a professor in this field? How do I get funding? Things like that. The career advice that could help you. And those meetings will have refreshments. So if you're here for the refreshment, also come to the 3 p.m. meetings. And another new addition this semester is that we're going to have our last colloquium of the semester is going to be a student colloquium. What does it mean? That instead of bringing a professor or an external speaker from elsewhere, we're going to honor our own students and postdocs, students in advanced stages or postdocs, and let them give talks. So this will give you an opportunity to appreciate the work of our own students and also learn from people who are down to earth about what they're doing. In terms of the attendance, every seminar we're gonna count attendance twice. First time at the beginning of the seminar and the second time at the end of the seminar. And this will count for your attendance. I will show a barcode now, and we will show a barcode at the end of the seminar, and this is what we're going to do every week to count your attendance. All right. Any questions about administrations, comments, concerns? All right. If you have, again, any further questions, you can reach out to Shanae, and if she, for some reason, is not able to accommodate your needs, you can reach out to us. Okay, so before going to introduce the speaker, this is your first barcode for today. So I'll give you a couple of minutes to scan this barcode, and also let me know if it works. We don't want bugs in the first colloquium of the semester. Yeah. Yes, so I still see a bunch of phones and a bunch of computers. I don't know if you guys are scanning or you are just looking at your computer. Everybody finished scanning? Okay. So, yeah, if that's the case, then without further ado, I want to open the Zoom, and I want to introduce our first speaker. So, our first speaker is our own Dr. Vijay Shah. He's an assistant professor here in the department, the ECE department. He leads the NextG Wireless Lab, a research group at the forefront of innovations in next-generation wireless systems. He also co-founded a startup called WeSites, and it develops a large language model solution tailored for next-generation telecom networks. So his research focuses on 5G and 6G systems, Open RAN, dynamic spectrum sharing, AI, LLM, and more. He is a recipient of his funding sources include NSF and NIST. And recently, which was a very, very impressive accomplishment, he won the NSF Career Award, which is a fantastic award for young researchers. Yeah, so Vijay, the floor is yours.
Thank you for the kind introduction. Can you all hear me? All right. And by the way, we are also down to earth. Okay, not just the students and postdoc. So this is one of the largest class I have ever been in front of, which is amazing. Yeah, go ahead. Okay. All right. So I guess here you can see, right, my primary appointment is being a professor in the EC department. And then I have a few other hats that I wear. Before I start, I would like to understand the dynamics of my audience here. So how many of you here are graduate students? Please raise your hand. Oh, amazing. And how many of you are undergraduate students? Okay. And basically the others, I guess, are colleagues here. Oh, that's amazing. Okay. Oh, this should be of interest to you. So, okay, how many of you are PhD students? Awesome. All right. I love PhD students. Okay, so we are going to talk about AI native telecoms. Today, AI is everywhere, honestly, so telecom is no different. And we are obviously pushing the boundary. As of today, I would say telecom is kind of slow in adopting AI for various reasons, and potentially you'll figure out through this presentation. But NVIDIA is pushing for it, so sooner or later, it will potentially happen. All right, so let's get started. So here is a quick agenda. I doubt we'll be able to go through all of it because I thought I had 1.5 hours, but I only have 1 hour, so we'll see how much we can do. The overview of NextG Lab research, I'm going to put that towards the end. What I'm going to do is quickly get into the topic of Open RAN, and then I'll cover a few important topics that came out of our lab and actually my startup company, which is the Neural Smith. So I'm going to talk about that too, but the other is from the research lab. All right, so to understand Open RAN, we need to understand a cellular network. So irrespective of whether it's a first generation of cellular network all the way to 5th generation of cellular network, which is the case today, the fundamental structure is still the same. So as you can see here, we have this mobile core on the top. This is kind of the bridge between your cellular network and the internet. It also builds you, it also tracks you so that it can provide coverage irrespective of whether you are here in Raleigh or somewhere in Ukraine, okay? So this is the entity that gives you that connectivity all the time. So that's the mobile core, but we are not gonna talk about that today, okay? The second one is the radio access network. So this is basically the infrastructure that you see deployed, let's say on the side of a road, like a big tower. You potentially should have seen those structures, not very pretty, but it's there to provide you coverage. Or on the top of a water tank or on the top of a building. I believe some of the building here at NC State also has these antennas or these towers. So together, we call them radio access network. So if you want to provide connectivity to the entire country, you have hundreds and thousands of these radio access network devices called base stations. And in wireless, we have a lot of acronyms. So just try to get used to it a little bit at least. So we call it RAN, and that's where the RAN word comes in the context of Open RAN, right? So now you can see that there is already a RAN. We're trying to make it open, okay? And we'll get to that. And finally, we have this user equipment. And again, from the name, it's the equipment that a user have to connect to the network, okay? So irrespective of what you use to connect to the network, whether it's a smartphone, whether it's a smartwatch, whether it's your refrigerator, whether it's your toaster, it doesn't matter. As long as it connects to the wireless network, we will call it user equipment, okay? So it's very clear now, right? So you have a device, every human, not just humans, there could be machines that could be connected to wireless network now, right? So anything that connects to the wireless network or the cellular network particularly, we call it user equipment. And why would you connect? So that you can send and receive data. So that layer of devices that gives you connectivity is called the radio access network or the base stations. And then whoever gives you access beyond to the internet, because eventually everything goes through the internet in today's world, right? In cellular, everything goes through the internet. In old days, at least the voice used to go through a separate infrastructure, but now even your voice calls are internet packets, okay? So that's the kind of the structure there. So now we are only gonna focus on RAN, because that's all I know. All right, so in RAN, the older generation of RAN, I hope we understand the term RAN now, right? So the older generation of RAN supposed to be or used to be very monolithic. It used to be one big device that you purchase from one of the three vendors, which are Nokia, Ericsson, and anybody? Go figure out. So there are the three vendors. So none of them are US vendors, but you go and purchase it from them, you deploy it. Yes? No. We do not talk about Huawei in this country. So that's the fourth vendor, but there are only three vendors in this country, okay? So not Huawei. What? No? Sorry? Samsung. Yes. So Samsung, Ericsson, and Nokia. They have the full monopoly of this market, about 90%. And usually, at least all the US operators today, AT&T, Verizon, T-Mobile, and potentially Dish Wireless, they all go and buy equipment from these companies, okay? One of these three vendors, not the fourth vendor, okay? So again, this is very inflexible because it comes from one vendor. It's very proprietary because it belongs to those companies, right? So it used to be the case, very easy to at least deploy, but very costly, okay? Billions of dollars. So that's why these guys, these operators, they said, okay, we need to break this ecosystem. We need to bring competition into the market. And that's where they started with this 5G that let us try to virtualize some component of RAN so that other players can come into the picture, right? And US is a leader in virtual systems and software, right? We have the biggest company in form of Microsoft and Amazon AWS and whatever, right? So we are the leaders in the field, so that also helps with the US security and US leadership and everything, right? So that's the reason why we said, okay, in 5G, we are not gonna go with those proprietary devices anymore. We are going to disaggregate the RAN into reasonable component, and as of today, we disaggregate into three components, which are called the radio unit, which is usually the hardware, and the very low layer analog to digital conversion and digital to analog conversion, right? Because the cellular are RF signals, right, which is the analog signal, but we do not process analog signal directly. We convert that into digital signals, right? So these things happen in the cell site, or the radio unit, we call it, and then we have the distributed unit and central unit, and that's what comprises the whole RAN pipeline. But it's not a single device anymore. We have disaggregated them. And because we have disaggregated them, now they are very flexible, right? You can mix and match. Like the vendor A, you can get the central unit from vendor A, the distributed unit from vendor B, and RU from vendor C, right? And it will still work as long as they follow the ORAN principles, okay? So, and because we have virtualized them, it's very programmable now. So that kind of brings the concept of Open RAN. And as you can see, a little bit of history here. So Open RAN was founded by these big 5 companies across the globe in 2018, so just before 5G happened. And that's potentially the reason why we do not see a lot of ORAN deployment in 5G today, except this wireless. But it will happen. So for example, AT&T signed a $14 billion contract with, that's weird, with one company, Ericsson, to deploy an ORAN network in December 2022, okay? Which is weird, right? Because we wanted many companies to be a part of ORAN ecosystem, but they went with just one company. And you'd potentially figure out why once I explain the Open RAN architecture. So here are the 2 core principles of Open RAN. One is openness, obviously, and openness comes from open interfaces, like, for example, between the DU and CU or CU and RU, even the open softwares or open servers, right? So we run this component on any COTS servers. We don't have to go purchase proprietary server from those companies anymore, okay? And then we can have open APIs, right? Now, because these are all software, you can literally access them through application programming interfaces, right? We adopt 7.2x split, which means that the physical layer or the lower physical layer would be at the RU itself, at the cell site, and then from there, you put it in the DU and so on. So it's not that critical, but just to get an idea. All right, so now let's go through this Open RAN at a very, let's say, high level, right, so that we understand. So here you can see at the bottom, this is your open radio unit. This is, as of today, is still hardware, is still proprietary, and is still at the cell site, okay? But except this, the DU, the open, O stands for Open RAN, the ODU, this will be at some server, okay? And not very far, it will be at an edge server because latency is a big issue. But it is completely on server, open server. And then we have the centralized unit, which will also be on some server, fully virtualized, but potentially at some regional server, not too far, because again, latency is an issue. And this could be controlled through this open interface. Why? Because we want different companies to come into the ecosystem. So if you want different things to come into the ecosystem, you have to standardize things, right? Think about your laptop, for example, right? Your laptop can connect to any keyboard, any mouse, any desktop, right? Why? Because the interfaces are very standard, the USB 3.0 or whatever that could be. So that's what we're doing here. And then in addition to this disaggregated RAN, we wanted to control this RAN component, right? Now that they are softwares, they're accessible, you need to orchestrate them. You want to deploy intelligent logic into those things, right? So because of that, we introduced something called RAN Intelligent Controller, or RIC, okay? And just based on the timing at which you want to control the component, we divided that into 2 components, the near real-time RIC, which is less than a second, so somewhere between 10 milliseconds to a second. And if that's not too time critical, then we put them somewhere in the remote server, potentially on the network operator's remote server, that is non-real-time RIC. So anything beyond 1 second is on the non-real-time RIC. So once you have this near real-time RIC, for example, now you can deploy software applications, okay? So the application that we deploy in near real-time RIC, we call them xApp, where X stands for extended applications. And you can see why, right? So you are extending the RAN logic, right? And implement it as a software somewhere in the near real-time RIC, okay? And it could be AI, it could be optimization, it could be something else. Maybe you can build a company on this who is just deploying xApps for certain network operator. Like, for example, you have a very cool algorithm that nobody has thought of, you can definitely do that. And I know a couple of companies who does that. So AirHub Communication is, for example, one of them. Then on the non-real-time brick, you again can have application. Let's say you want to, allocate more bandwidth to NC State now than 10 years ago, because NC State has more students. You need to support more students, and they're doing a lot of AI these days, right, for homeworks or whatever, right? So we need to support that bandwidth, right? So in that case, you might be allocating more bandwidth, which doesn't happen every second. It happens over a period of time when human user behavior pattern changes or the density changes, right? For example, Raleigh is one of the biggest city in the country, right? So more and more people are coming in, so we need to deploy more and more base station or allocate more and more bandwidth to each base station, right? To support more and more people. So those things do not happen every other day, right? So those things you can do at a much lower scale, and the applications we deploy there are called RApp, and R stands for remote. And you can see why, right? So that's the idea. Now, on top of that, so this is what O-RAN Alliance or the industry already has adopted. But this one, the real-time brick, we are expecting that we can also control the RAN functions which operate at milliseconds or sub-milliseconds. Industry hates this idea, but academic loves this idea, so we are working on that. Okay, and I'll show you some example. If you want to learn more about it, you need to go purchase a book that I co-authored. Okay, it's called Fundamentals of O-RAN. All right. So that's all the background there. All right, so one last slide on background. I hope those made sense. If not, think in this way. I'm sure you all are familiar with computers, right? The computer that you use every day, right? In fact, every device in today's time is a computer in some way. Okay, it's a customized, miniatured, but it's still a computer, right? And what exactly comprises a computer? Think about it. So computer is nothing but a bunch of applications, software applications. It could be a browser. It could be your, let's say, Microsoft Word. It could be TikTok, right? It could be anything that you run on a computer. And then, obviously, computer runs on certain hardware. Like, let's say you have disk, 1 terabyte of disk or whatever, or CPUs, right? Now we have so big RAMs these days. Then you definitely want to access the network, so you have network sockets and so many different hard drivers and so on, right? But the applications, let's say you want to be an application developer. So when you develop an application, are you going to go right to a specific memory in a specific disk? No, right? What you do, you use a programming language like C, C++, or Python, whatever. You implement your application using that high-level programming language, and then operating system makes sure that your application gets what it needs, right? Let's say you say, I don't know, create a list or create an array, right? So when you create an array, it's going to get stored somewhere in your RAM or somewhere in your disk, right? So who is going to take care of that? Obviously, the operating system, right? So operating system actually made all the difference in the global adoption of computers. If you think about it, right? Before these two big guys came through, the Apple guy and the Microsoft guy, we used to have mainframes. And IBM predicted that there will hardly be 20 computers in the entire world. Today, every house has 20 computers, right? So this is amazing. The similar thing happened with network to a certain extent. You know, in 2000s, about 2 decades later, we say, you know, we don't want our routers to do everything for us. Let us separate the logic and implement them as network applications on some high-level server, and then our routers or switches would be very dumb. They will simply do what the application asks them to do. So just a switching fabric, right? So that's what happened with software-defined network or the internet. And I think we are going through a similar paradigm shift in wireless network because of Open RAN, okay? So in Open RAN, we will also have applications, our own application, wireless application, let's say RAN slicing or load balancing or whatever, and we have our own hardware, which is the antennas, the radio front end, and so on. And similar to what operating system did to computers, or network operating system like SDN controllers, ODL, if you're familiar with networks, you should be familiar with Open Daylight, right? Or ONAS. The similar thing is going on with RIC. That's again, don't go and fight with anybody. This is a term I use, okay? The RAN operating system, but you see the analogy there, right? So in a way, we are going through that paradigm shift in the cellular network or wireless network. It's just that we are 40 years behind computers, okay? So I hope this makes sense, this kind of position Open RAN and RIC in the scheme of things in the computer world, okay? So if that makes sense, now let's see where is the ORAN community interested? What are they doing, right? And obviously, this is my biased view because obviously I'm presenting. So there will always be a bias. So to my, let's say, to my bias, I think the most interesting topic today is to build those software applications, okay? Again, think about computers, right? What do people do with computers? Build and use applications, right? That's usually what nobody thinks about operating system. Nobody thinks about, disk. I mean, some people do, but most people think about software applications, right? And that actually is highlighted in top 500 companies. Go look at the top 20 companies. They're all computer software companies, right? So again, I think similar thing will happen with the wireless world. We'll focus a lot on applications, and because of the AI resurgence, a lot of AI applications, okay? Then the testing becomes a big part, okay? So in old days, in the remember the monolithic proprietary RAN in old days? So there the testing was much easier, right? If something goes wrong, you go to one of those 3 vendors and say, fix it, right? And then they will definitely make sure that their system works before they ship it to their customers, right? But now with Open RAN, that's not the case anymore. You get an RU from vendor A, DU from vendor B, CU from vendor C, near real-time rig for vendor E, non-real-time rig for vendor F, xApp from vendor G, RF from vendor H, and so on. And there could be hundreds of xApp and hundreds of RF, right? So who is going to make sure that this big, complex, messy system that you have created works all the time? So testing becomes really, really important. Operator is not going to do it. The vendor is not going to do it. Then who is going to do it, right? So that's where the testing is a big thing. And that is the reason why AT&T signed a $14 billion ORAN equipment purchase just from Ericsson, right? Because nobody wants to do it, right? So, but at the same time, they want to have the leverage. So if it is ORAN compliant, if they don't like it, they can always switch back, assuming that the testing is much more mature by then, right? So that's, I think, the second very important topic. And then there are some notable topics. The reason they are gray out because I don't work on them. So we're going to skip it. And the last one is the ORAN privacy and security. This is also very important, right? Now think about those N number of vendors we brought into the ecosystem. We have made the interfaces open. We have made the software open. You have made the servers open. So obviously there will be bad guys, right, who will explore this expanded attack surface, right? So who is going to fix it? How are you going to fix it is an important problem. But at this point, nobody's really supporting this in a big way. But sooner or later, we will have to, okay? All right. Now let's talk about the applications, right? So in the scope of application, RAP is extremely, RAP is gaining a lot of traction from the industry, whereas academia is more interested in xApp. And there is a good reason why. The reason is, if something goes wrong in an xApp, the operator would not have the time to fix it because it runs in sub-second, right? And if something goes wrong, the only entity that's going to lose business and and goodwill is the operators, right? So they won't take a risk until and unless they have sufficient evidence that the xApps work, right? But the RApp, the good thing is they operate in hours and days and months. So there, even if something goes wrong, you still have time to fix it, right? So that is the reason why the industry today is mostly interested in deploying RApp rather than xApp. So we have developed a number of RApp and xApp in our lab. So here is a list of those xApps. I'm not going to talk about all of them. Maybe I can very briefly cover one xApp, and then we'll get into some other topics. How much time do we have?
So half an hour.
Oh, OK. All right, so let's talk about the first applications, OK? So it's called a Spark, multi-site spectrum management in communication network. So a little bit of background here. So what does a cellular network or a wireless network should support, right? So obviously, we want to support a lot of emerging applications, right, which could have a lot of different bandwidth requirement. So to do that, so here is a plethora of application or a number of applications with very unique requirements. Think about autonomous vehicle, for example, or remote surgery, or your AR, VR handset, right? They all have very different requirements, right? A VR would require gigabits of data rate, whereas an autonomous vehicle does not require gigabit of data rate. But what they require is an ultra low latency and ultra reliable or ultra reliability because they are very safety critical, right? So if I lose the data to which command to hit the brake, that's not acceptable, right? So again, those are the applications we want to support, right? The wireless networks wants to support. Now this requires, obviously the spectrum is kind of the engine for wireless network, right? Which is the radio frequency spectrum. So that is not infinite, right? It's limited. So how are you going to use that spectrum so that you could support these newer and newer applications and billions and trillions of devices because of IoT and because of every other thing being connected to the internet now is an important problem. So now a spectrum is complex, it's limited, and here are some examples. They do get interfered, they do get congested, they do get contested, right? So, and then, like I said, the licensed spectrum is limited, right? So how do you manage this spectrum is a big problem, right? And that's the kind of problem we wanted to address. And here is an idea, right? To manage the spectrum better, we have to monitor the spectrum, first of all, right? Otherwise, how would we know which part of the spectrum is congested, whereas the other spectrum is completely vacant, right? Or not, or is underutilized. How do we know that? So to do that, we have to somehow monitor the spectrum. And also, you will have to distribute the spectrum across multiple such base stations, right? Because remember, we have these thousands of base stations who provide the communication to the users or devices using this spectrum, right? So it means you have to allocate resources to these base stations without creating a lot of interference among them, right? So for example, if you have two base stations in this room or two radios in this room, they cannot operate in the same spectrum at the same time, otherwise it will create interference, right? Unless you come up with something more interesting to address that problem. So that's kind of is the motivation for this work, that can we intelligently redistribute a spectrum across multiple such base station sites based on the application traffic demand and the spectrum conditions, right? So think about these two base stations again. Here, let's say there are only 3 users who are connected to this base station, but there are 100 users who are connected to this base station, right? So as of today, usually we allocate, let's say n number of spectrum channels to each of the base station, but that's not a good use or an optimal use of a spectrum, right? You want to allocate more spectrum to this guy because there are 100 users and less spectrum to this guy, right? But if these guys move here, then you want to allocate more spectrum to this guy and less spectrum to this guy, right? So this needs to be very dynamic. And that's where the Spark comes in. So here is a motivating example. So let's say this is an indoor smart warehouse like an environment, right? In a smart warehouse, obviously you have to deploy a lot of RUs, a lot of antennas, and you cannot really ask them to operate in different spectrum at the same time because the spectrum, again, is very costly and very limited. So usually, as of today, most of the industry deployment have like 40 megahertz of channel that they have license for. Again, these licenses goes in billions of dollars, by the way. Okay, and that's one of the reasons why your cellular network is so expensive compared to Wi-Fi. Think about it. Wi-Fi operates in unlicensed band, so there is no overhead of those billions of dollars to just secure license to operate your device or network. So here is the proposition that let us deploy these RUs so that they can give you better coverage. Okay, they can handle more and more users. But let us allow them to use the entire spectrum, okay? And you cannot just do that because it creates interference, right? Inter-cell interference or inter-site interference in the typical way. But we propose solution that will address that problem, okay? That inter-cell interference. So that's where the real-time resource distribution comes in, where we dynamically allocate resources at each and every site based on these two requirements, which is traffic and the channel conditions, okay? So that's where the whole, let's say, USP of this work is. So to do that, we could not work with the existing O-RAN ecosystem. We had to expand or extend that work a little bit. So let me show you how exactly it works. So this is just the RAN network, right? You are familiar with CU and DU and RU now. And this is maybe I'll use annotation a little bit. And this is your non-real-time break and near real-time break, right? So they are able, this is what is today's O-RAN system, right? I have already explained this at a high level. But this was not enough because we had to manage the spectrum resources in real time, not in near real time, okay? So because of that, we had to introduce something called EdgeRIC, which actually run applications in sub-millisecond, okay? And this allows allocating resources in sub-millisecond. So basically, the platform here, the Spark, they can handle dynamic environment changes as long as this is in sub-millisecond. If it is nanosecond, then that's not possible. And then our platform is a standard O-RAN standard compliant with additional extension to the platform. So with that, yeah.
I have a very basic question.
Yes.
You're talking about scenarios in which the hardware has already been deployed and you're trying to optimize the resources in order to, fulfill the requirements of all your customers or whatever. But are you also looking into how to deploy the hardware optimally in the first place in order for your techniques to be better?
So that's called network planning. We definitely do that. Nobody goes and deploys this hardware randomly. So a lot goes into that. Yeah, but even after that, there are so many dynamic factors like user traffic, right? How would you predict beforehand that who is going to watch a lot of YouTube videos in this NC State campus and who is going to use a lot of AI applications? Who knows, right? So to address those problems, we have to manage, or we have to do this management after the network is deployed.
But the same management you specifically, or?
Oh, no, this is the network. No, we did the research, but network operator will manage the resources. Okay. Yeah, so this is how it's going to work. So basically, we'll have this near real-time break who will run an interference detection and localization xApp. Why? Because we want to understand if there is some internal or external interference going on at each and every cell site, okay? Once we understand that, it kind of gives us an idea what are the resources that I don't want to use at that site, and what are the resources I want to use at that site, right? So that's the idea of the xApp, and this can happen in tens of milliseconds because you need to understand the trend as well, right? And the second one, which is interesting here, right, that once you understand that, then you can basically say that, okay, at site 1, I'm going to use this resource here. At site 2, I'm going to use this resource. And at site 3, I'm going to use these 3 resources. Why? Because you potentially at site 1, you don't have enough traffic, so 1 resource is enough. And then this is probably the best resource there. And then at site 3, maybe there are so many traffic, you need to allocate more resources. But these resources are more noise-free, for instance, right? So this is the whole idea. And let me also show you how it's supposed to work. So for example, let's say this is your entire spectrum that's available to you, okay? So now let's assume that there are 2 sites. So one site tells me that there is some kind of interference going on here, okay? And then the other side tells me that there is some interference going on here. So what the approach does, it says, so this is what the xApp does. xApp goes, detects, and localizes the interference in the entire spectrum, right? So this is the xApp kind of tells me that. Once it is known to me, then what I'm going to do, the mu app, mu stands for microseconds, by the way. So the mu app goes and allocates resources, the best resources at each and every site, okay? So that's the overall working. I'm not going to go through algorithms now, but let me show you a quick demo. So this is the overall system implementation that we did in our lab. And then maybe before I go to the demo, so this is the overall time we compute, let's say recorded for the xApp, which is under a second, which meets the ORAN standard. And then this is under, again, some 100 microsecond for the mu app, which also meets the requirement of our application. And then it shows that we do better than existing resources, but let me again show you a demo here, right? So this is something we developed in the lab. So as you can see here, we have this little own private 5G network. So this is, let's say, RAN site 1, and these are some of the configuration we use for the 5G network. And then we introduce a jammer so that we can create interference in the environment. And then you'll see some interference there, right? And then that IC xApp is basically interference classification xApp that I already mentioned to you. And then you can see when the interference comes in, you'll see the packet error rate goes high, right? Or the SINR reduces. So once the IC xApp is activated, it blanks those resources, or it kind of localizes and blanks those resources. Now we extend that to two sites, right? Because we wanted to understand what happens when both the sites operate in the exact same spectrum, okay? And what we do at the site 1, we stream a lot more traffic, let's say 25 Mbps, whereas at site 2, we stream much smaller traffic, right, 5 Mbps. So the Spark is able to identify that and see, remember at site 1, we had a jammer operating here, so that's why we kind of blanked that, but at site 2, there is no such jammer. So that's why I'm able to allocate more those spectrum there, and also looking into the traffic, right? Because you had fewer traffic, I give them less spectrum resources, and so on. So now I'll keep changing the traffic. Let's say 2020. Later I'll change it to 525. So you see how it's able to do that in milliseconds level, which is the time granularity for 5G operations. So 5G today operates every millisecond or every TTI, we call it, a time slot. I mean, it does allocate other flexible time slot, but for now we'll stick to 1 millisecond. All right, so that's a little demo there. Now let's talk about AI ML itself, right? So AI, by the way, I don't know why people use these two terms together all the time, right? AI ML. I mean, ML is a subset of AI, right? But people use it, so I also use it, but it's basically AI, right? So AI, will be native to 5G or wireless, right? And probably to other domains too. And in case of ORAN, obviously the xApps, the RFs, the mu apps, right? Those things. But there are a number of challenges when it comes to AI itself, okay? So for example, our microseconds operate in milliseconds, right? So our AI model needs to operate in milliseconds. How many AI models do you know which give you inference in a millisecond, right? So that's a problem. So we have to design AI not for accuracy, but for problem solving, okay? Even if it's not too accurate. We need to optimize our AI ML platform, which is the RIC in this case, right? Because there will be hundreds of xApps and hundreds of RApp, right? So you cannot train and allocate compute and allocate memory to each and every xApp. There is not that kind of compute available at the base station, right? It's probably available at some server, and you have billions of dollars to support that, but not at the base station, right? So how do you make that work? Also, the last thing that I mentioned, right? The xApps and RApps, especially the xApp, the operator is not willing to deploy them today. It's because you do not trust them, right? And machine learning doesn't help, right? It works at times, but it doesn't tell you why it works, right? It doesn't explain you why it works, right? With the older approaches, the model-based approaches, you know why it works, right? Even in the worst case scenarios, it will work with a certain guarantee. With AI, it can give you 100% and it can give you 0%. You don't know, right? So now to address that problem, you potentially have to test a lot. And in wireless, it's a very big problem because your environment can change from Raleigh to New York downtown, right? So how do you test your model, which will run anywhere in this world, is a very big problem, okay? So, but we need to do that, okay? If we really want to deploy AI into wireless. And the last one, designing AI is not an easy task, right? We are not ML people, right? And many people are not ML people. We all leverage AI, but we do not build the best AI. We cannot, let's say we do not know whether we have built the best AI. Let's say as a graduate student, I say, okay, go solve this problem using an AI. What would you do? You'll potentially go find something that potentially makes sense. Let's say your data is a bunch of images, right? Then you'll potentially go look at some CNN models or some, let's say, AlexaNet or whatever that is, right? And then you'll potentially train them. You don't even know whether you have overtrained them or undertrained them. As long as you get a 99% accuracy, you are happy. But you don't know, right? And you don't have enough data or let's say you don't have enough time to do that. You want to publish papers, right? So again, this is a problem. How do you do hyperparameter tuning? How do you do data pre-processing? It may take weeks and months, sometimes several months. So we try to solve that problem. So where we introduce something called Neural Smith, okay? So we try to make sure that you are able to get the best model without going through all that issues. So the way it works, let me give you some key features here. So we support data set in any format with any directory structure. We do the pre-processing for you. And it's a very simple process. We do the planning, we do the code generation, we execute, we show you how it works. I'll show you a little demo. We also do the error handling. We also have guardrails to make sure that your data is not lost or not stolen. And it's fully interactive. So here is a little demo. So on the top, if you see, we are going to go through the directory. It's a little fast because it takes about a few minutes. And then it's generating a plan for whatever data set that you're working with. Once you have the plan, if you like it, then you say, okay, let's proceed with the code. And this is on top of VS Code, if you're using that platform. All right, in the interest of time, I'll go through that. So now here, if you see, now we have generated the code for you. Once the code is generated, then you can go into the training phase. And again, this is all through chat. So it goes through the training phase. It trains the model in front of you. It tells you how it's going through different hyperparameters, tuning, and stuff. And then, once it is done, you will have the fully trained model. And so far, as per our rigorous evaluation, we are matching the state of the art. Just give me a second. I schedule a meeting at 11. All right, so that's...
Platform has anything to do with ORAN? Or
No, this is complete AI ML platform. And we are actually looking for beta users. So if you are interested, I would say go in there and join our beta waitlist. We want to see what's the experience with whatever data set you are working on, okay? All right, so now let us talk about ORAN side. Let's come back to ORAN. So in ORAN side, this is something that we developed for ORAN. So we call it foundational LLMs for ORAN. So we started, actually when we started this work about a couple of years ago, there we noticed that existing LLM do not work with very specialized topics like ORAN because they do not understand ORAN concepts or ORAN specs or ORAN code, right? So for that one, we say, okay, let's try the simplest and the most easy approach called retrieval augmented generation, or the RAG. So what we did, we used the existing model, and then we basically feed the ORAN specs and see whether it could do better. And we actually saw some improvement. We saw that we are able to beat, at least at that point of time, the ChatGPT and the Mistrals and the Gemini on different level of difficulty of ORAN questions. So we already saw some interesting result there, but the problem with the RAG was that it did not work with our code, with our source code. So for that reason, this is just some generated questions and sample. For that reason, we introduced ORAN Site 2.0, where we do not just rely on RAG, but we actually start with open source model and fine tune them to work with ORAN source code and ORAN specs. Okay? And to fine tune them, we had to develop a RAN struct framework which works on this data set. So here are the key data set we use. There are this ORAN specs. At that point, there were 116. Now I believe it's more than 150. The 3GPP, these are the cellular specs or cellular standard documents. So there is about 15,000 such document. And then SRS-RAN is one open source implementation of 5G. And then there is another one called Open Air Interface. So we haven't worked with the Open Air Interface yet in ORAN side, but we have worked with SRS-RAN. And by the way, these models are publicly available on Hugging Face if you wanna give it a try. And then the data set that we tested on is also available on GitHub. We are working on the reasoning model right now, which will be available very soon. So here is the little pipeline of how ORAN site works. So we start with this 5 most prominent open source model. We cannot work with proprietary model because they don't let you change their model parameters or anything. So we had to work with open source model. So like we have this Queen, Mistral, Phi, Llama, and Gemma. And we worked from 1 billion parameters to 70 billion parameters. Now we have trillion parameter model. The problem is I don't have, or I'm not rich enough to have enough GPU resources to run them. Okay, so that's why we had to stick to 70 billion. And then once we have the model, then we basically have to create our data sets. So we use ORAN Alliance or those ORAN specs, and we use SRS-RAN code file. We pass them through RAN struct framework that we develop. And then this gives us this fine-tuning data set. And then what we do, we retrain those LLM models with our data set, and that's when it becomes the ORAN site version of Queen and ORAN site version of Mistral, and so on. And then we tested them against these 2 benchmarks. That's how ChatGPT publishes at times that we are better than other models on this data set, right? Remember, so if you see their web page, you will see that all the time. They have like bunch of data set, and then they compare everybody's performance on those data set. Like like language or math or something, right? So similarly, for 5G or cellular, we have these two data sets, O-RAN bench and SRS RAN bench. So by the way, we created this data set because there wasn't any. But it's publicly available and open to anybody who wants to beat our models. So there are some more detail, but in interest of time, I'll skip them now. But let me show you results here. So as you can see here, we compared this against the best performing model for ChatGPT and Gemini at that point, at least about a year ago. And you can see that we, at least some version of ours, let's say O-RAN side Gemini at 27 billion, it does the best in SRS RAN bench, whereas O-RAN side Queen does the best in terms of O-RAN bench compared to the models. We also compared this with some existing telecom models. So there are a couple, like NVIDIA created an O-RAN chatbot. Then there is Tele LLM from Yale and T-Spec LLM from Khalifa University in Saudi Arabia, I believe. So we are beating them, all of them, by at least 28%. So here are some generated questions on the code. And then I skipped it, but there were some questions on the O-RAN specs. And there is a little demo on how O-RAN site works, for example. I haven't made this publicly available because it costs money, and we don't have the funding to support hundreds and thousands of users. So unless somebody supports, it will not be made available. But the models are available. So if you want to use your own GPU resources, you can always download the model and try it out. So this is on the simple textual queries. You can also generate code. This is not perfect, but we are working on the Copilot for 5G. So hopefully soon we will have a Copilot that works well with wireless. We have tested Cursor AI and Windsurf and GitHub Pilot and there is one from, I'm forgetting the name. So we tested them. They do not work very well on O-RAN and wireless. So we are building our own Copilot on top of them. We don't want to duplicate stuff. So we are going to basically extend their capability with wireless to create our own Copilot. Similarly, you can also actually upload images, like O-RAN images and wireless images, and then you can basically ask questions. And it will give you responses because our O-RAN side model understand the O-RAN jargons, the cellular jargons, the 3GPP specs, as well as we have used this vision model who understands the images. All right. I think I'll stop here. I'll skip this one. All right. So here, let me quickly go through the NextG Lab research. Even though here I talked a lot about O-RAN, and you see why, because this is a big topic in my group. Within O-RAN, I kind of covered the AI, xApp, RApp, right? At least the Spark work. And then I did not cover the O-RAN testing, where also we use a lot of AI to make O-RAN testing much faster. So as of today, it takes weeks and months to do testing. We build AI 5G test that does testing within 45 minutes. Right now, we are working with this big testing center in the country, like Valor, led by Dish Wireless, and Orchid Valor led by VRV, and Dish Wireless led by Orchid led by Dish Wireless. We're working with them to integrate our platform into their testing center so that we could make them much faster. You already saw the O-RAN side. That's the LLM work we are carrying out. So we are now, so the O-RAN side is mostly, let's say, an assistant of O-RAN or wireless, right? So it kind of helps you write code, helps you understand the spec. But now we want to leverage those capabilities to solve O-RAN problems, okay? So we are working with how to design better rig platform instead of doing these individual ML models for each and every task, right? Or how to do a spectrum sharing. Then we have some other tasks like positioning and sensing, spectrum sharing, satellite network, beamforming, and lunar 5G network. The common denominator across all these topics is Open RAN. We do use Open RAN to prototype whatever solution we come up with. And I obviously have to thank my very awesome team, without which I will not be here and I will not be talking about all the research work that we are doing, and the collaborators. So this is the concluding slide. So Open RAN will, at least in my view, will definitely transform the wireless space. Now, how open it will be, that's a question for debate. Like, think about computers, for example, right? We have Microsoft, which is completely proprietary. We have Mac OS, which is built on top of open source, but is proprietary. And then we have Linux, which is completely open source, right? So I think we'll have similar model for RIC in ORAN space. So, but the good thing is that the features that it brings, the softwareization, the virtualization, that's not going anywhere. Okay, that is going to stay, okay? So ORAN, in a way, again, will serve as an operating system. And now, instead of taking a decade to get to 6G, which is 2030 in this case, it might just be software update, okay? So with that, one last comment. Software is eating the world. There is no doubt, there is no debate on this, irrespective of what you are doing. And AI is eating the software, so AI is eating the world. So telecom is no different. Thank you.
All right, questions? Abby?
Yeah, so I have a question about if you have a system that's allocating spectrum to different base stations based on the demand of those base stations, is there a constraint in terms of the hardware at each base station and what it can handle, what bandwidth it can handle? So
Yeah.
it can only handle 3 to 5 gigahertz. You can't allocate it 1 gigahertz.
Yeah, for sure. Yeah, you can only play within the rules of that hardware.
So that's another factor that's being considered.
Oh, yeah, so we sort of assume that those are the given constraints. So whatever optimization we do, that's within those constraints. Yes.
Right, other questions?
All right, if not, I will run to my meeting.
I'm just launching the barcode for you all.
All right, thank you guys. Thanks for listening to me. Oh, by the way, I'm offering a course on ORAN. If you're interested, you can always reach $5.90.
All right. Yeah, we can stop. Wait, which button? Ah, this one. All right. Second barcode, guys, don't forget. What's going on? Okay.
So it should work. Should it open at 11 and then close at 11:40?
There's a lot of
So they
stuff that I need to add. So the
Yeah, I
problem
mean-
is this thing is very hard
We're doing good on
to
time.
grasp because there's a lot of parts. I'm trying to make it visually, otherwise
Yeah, guys, if you finish scanning, you are dismissed, unless you want to ask us some questions. Anyone else needs to scan? Okay.
It was okay, right?
What do you think? Now we solve the issue of this.
Yeah. I mean, then we're not going to have any issues to speak. Right. You just need somebody here to turn on the Zoom on the computer, one of us or the host. Oh, the host cannot do it. One of us or Shah.
That's the question. This is on the roof or sheet, but this is.
Shanae. Okay. Please.